Welcome back to our astrophysics lesson series. Today, we're going to start applying the things that we've already learned, including Newtonian gravity and general relativity. If you want a refresher or you haven't seen those videos, check them out on my channel. The first thing we're going to tackle is dark matter. In 1932, Jan Oort measured the speeds of stars in the Milky Way galaxy. They were moving far too fast based off of the theories of gravity that had been proposed. General relativity and Newtonian gravity both dictate that speeds of orbiting masses must be just right to allow the mass to stay in orbit. If an object is going too slow, the masses will collide. If an object is going too fast, the gravitational force from whatever mass it is orbiting will not be enough to keep it around, so it will fly off into space. When Oort did the calculations, he found that these masses should be flying away. There was not enough force from the gravitational center of these galaxies to allow the planets and stars to orbit at such high speeds. Since then, many other experiments like Oort's have yielded similar results. There are two schools of thought surrounding this phenomena. The first is that our current models for gravity are wrong. Many of these groups have proposed altered versions of general relativity, Newtonian gravity, or vector tensor calculus. But none of these have serious experimental backing. The second, and much more widely accepted explanation for this phenomena is that there's more matter in these galaxies than we can see. We call this matter dark matter because we can't see it. If there was more mass in these galaxies than we can see, the gravitational force on the occupants of the galaxy would be higher, allowing them to move faster without flying out of orbit. So how do we know dark matter exists and our current theories of gravity aren't wrong? Well, dark matter has accumulated a significant backing of experimental evidence and is the most widely accepted theory. Gravitational lensing experiments that have been done since the development of the dark matter theory have helped scientists make significant headway in understanding this mysterious matter. A gravitational lens occurs when light that reaches the Earth has been bent by the gravitational pull from large masses between the Earth and the light source. Light bends when large masses, like a planet or a star, exert very high gravitational forces on the particles composing light, called photons. This can make other galaxies appear distorted, misshapen, and dimmer than they would had the light not been bent before it reached Earth. These experiments often produce much more gravitational pull on light than we would expect, which could be due to dark matter distorting the light. The cosmic microwave background of the universe also helps prove the dark matter theory. At the very beginning of the universe, everything was born in a tiny point of energy and radiation. This point began to expand slowly, and as it did so, it cooled. As it cooled, electrons began to bind to protons and neutrons, creating atoms. When an atom is created, it expels excess energy in the form of light. All of this light, or photons, were being produced in massive waves during this period. But the universe was still expanding, and it was expanding faster than the waves were moving, meaning that these waves are still around today. Though they are very small, they're still measurable. These waves are referred to as the cosmic microwave background of the universe, or the CMB. And measuring them can tell us a lot about the birth of the universe. We can trace them back to their place of origin. And what we see is that a lot of these waves are a lot bigger than they should be had there only been baryonic matter at the Big Bang. But with the inclusion of dark matter, these areas are much more likely to produce the high energy waves that we actually see. This experiment was a huge proof for the dark matter theory. Between galaxy speed experiments, gravitational lensing, and the microwave background of the universe, we're pretty sure that dark matter exists. The evidence is almost undeniable. There's a lot of things that we still don't understand about this mysterious substance, but there are a few things scientists have figured out. The first of these may seem obvious, but it's a pretty big deal. Dark matter is, dark. This means it does not interact with the electromagnetic spectrum. You can see me right now because light is being emitted from your computer screen. You can tell that this part of my sweater is pink because it's absorbing all other colors of light, but reflecting this bright pink back at the camera. These are just simple examples of normal matter interacting with the electromagnetic spectrum. Dark matter wouldn't do any of these things. Dark matter does not absorb, reflect, or emit light. This means that many of our standard methods for measuring cosmic movement are rendered useless because we cannot see it and we cannot bounce waves off of it. Dark matter is non-relativistic, a second quality that we know. All this means is that it does not move anywhere close to the speed of light. Light moves so fast that we have to study it differently, so it's important to know that dark matter does not move that quickly. The third quality of dark matter that we know is a rough estimate of its quantity. Dark matter is estimated to make up about 27% of the universe, though that number varies with experimentation strategy. Dark energy, which is a topic I will cover in a video soon, is 68%, and normal matter is the other 5%. This means that normal matter, or baryonic matter, which includes you, me, stars, planets, and everything you can see in the night sky, actually makes up a very small percentage of our universe. The term baryonic comes from a Greek word that means heavy. It was named this way because all of the atoms that had been discovered were much more massive than other non-atomic particles at the time. This baryonic matter seems to come in clumps, planets, stars, etc. But dark matter doesn't. It seems to be pretty evenly spread out. The fourth known quality of dark matter is that it is not in baryonic form. We know this because even dark clouds of baryonic matter reflect electromagnetic waves back at the Earth. Baryonic matter is everything on the periodic table. These are atoms with protons and electrons. Dark matter cannot be in this form because of its lack of interaction with electromagnetic waves. And that is about where the list of things we know about dark matter ends. So what are we researching? Scientists are currently working on figuring out what the composition of dark matter is. There are several particle options, but there are two that are most likely. Here they are. The first possibility for dark matter's composition are weakly interacting massive particles, also known as WIMPs. These particles were theorized long before dark matter. There are other physics theories, including supersymmetry and string theory, that both predicted the existence of this particle. Now, scientists think that it might be a perfect candidate for dark matter. Let's see how it holds up against what we do know about dark matter. First, these particles have not been discovered or proven to exist, likely because they do not interact with electromagnetic force. So far, that fits the bill. Secondly, these particles have mass. That is important because it makes these particles non-relativistic. Third, they are weakly interacting. This is important because it means they're unlikely to clump into planets or stars like baryonic matter. The models that predicted this particle before dark matter predicted that it would take up about 30% of the universe, which is about right. Fourth, this particle does not fit into the standard model of particles and is not baryonic in form. This seems to check all the boxes. The second theory for what dark matter could be made of is the axion. Axions are very low mass, uncharged particles. And if we take a look at the four main things we know about dark matter, it holds up pretty well. First, because of their mass, they are very hard to detect, which accounts for the dark quality of dark matter. They have mass, making them non-relativistic. We do not know how many axions exist, but we know that they would likely be significantly more dense than WIMPs. They are also proportionately less massive than WIMPs, suggesting that they may exist in about the right quantity. All of that is theoretical, however, because neither WIMPs nor axions have been discovered to exist outside of theories. And fourth, axions are not baryonic in form. However, they are much more related to the standard model of particles. Axions are distant cousins of the Higgs boson particle and likely break down into photons, the particles of light, in certain circumstances. Experiments looking for axions are trying to prove their existence via these leftover photons. There are a few other particle candidates for dark matter. They're just much less likely than axions and WIMPs. Massive astrophysical compact halo objects, also known as machos, are a possibility. This group includes large stars and black holes, many of which are difficult to see because of the Earth's gravitational lens. These are unlikely, however, because they are not evenly spread out and can interact with the electromagnetic spectrum. Gravitinos, a theorized particle that may create the gravitational force, are also a candidate. This model would potentially change the way our gravity theories work, and it has very little experimental or physical support, making it unlikely. The Kaluza-Klein particle is a particle that would exist in a fourth dimension. Though this particle is predicted to meet many of the requirements for dark matter, scientists would first have to prove the existence of this fourth dimension. This is a rather unlikely scenario. The type of particle that dark matter is made of determines a lot about the way that we interact with it. Some theories predict that dark matter is passing through you and me all the time, but that its particles are too small to ever interact with our atoms. Kinda crazy, huh? Dark matter is probably spread all throughout our lives, and we still have no idea what it's made of. Dark matter is commonly confused with antimatter, and it is important to understand that they are very different. Antimatter is like the opposite of baryonic matter, and they cannot coexist. Antimatter is made up of antiprotons, antielectrons, and antineutrons, the opposites of the particles in baryonic matter. At the birth of the universe, there were large sums of both antimatter and matter. Because they are antiparticle partners, when they interact, it leads to destruction of both particles. There was more matter than antimatter, so our universe has stable baryonic matter in it. There is no antimatter in the universe currently. Dark matter, however, is simply a different type of matter that can coexist with baryonic matter, though they interact very little with each other. Dark matter is also commonly confused with dark energy. The universe is expanding, and it's doing so at an accelerating rate. Scientists don't know why, but we call whatever's causing this dark energy. Dark energy likely doesn't have mass, and in a video coming soon, I will delve further into what we do know about it. But it's very distinct from dark matter. Dark matter does not cause the acceleration of the expansion of the universe. Dark matter and dark energy are frequently discussed together as two of the biggest mysteries of physics right now. And we use a lot of the same technology to study them, but they are two distinct things. The future of this theory is very exciting. The alpha magnetic spectrometer experiment is one of the many experiments that are trying to detect a dark matter particle. This equipment does that by measuring the cosmic rays on the International Space Station. Cosmic rays are just parts of atoms that have broken off and are hurtling around the universe at nearly the speed of light. Measuring these can tell scientists a lot about the nature of space. The CERN Particle Collider in Switzerland is doing several experiments to prove the existence of WIMPs and axions. They can measure the energy in the collider before and after colliding particles, and any seemingly lost energy may prove the existence of these particles.
Huge thank you to David Whitaker for helping me with this script.
Dark matter is a huge piece of the current physics research scene. In the next video in this series, we will be covering its counterpart in physics research, dark energy. I hope to see you then!